Thank you very much. I will go a little bit in more details with respect to what Francesca presented this morning about the EMM project. In particular, I will show you the lunar electromagnetic monitor in X-rays, or this idea. But I will start from a couple of astrophysical questions that arose in the last years. We got aware that the study of the universe into the time domain has become increasingly important, meaning that we need time-resolved wide field observation on different time scale, from very short, let's say from microseconds or milliseconds, to very long, tens, thousands of seconds. And this kind of observation already are we know that are bringing to light unknown transient phenomena like fast radio burst or other phenomena. On the other hand, as Jan was saying, the detection of gravitational waves and, for example, the discovery of their electromagnetic counterpart started a new era for astrophysics, where we now know that we shall merge electromagnetic observation together with gravitational wave observation and also neutrino astronomy. So the idea is that we need a high performance wide field of view X-ray monitor, which can provide us with prime observation of the violent sky, meaning in the high energy range from X-ray to hard X-rays and gamma rays. What we need a high energy band from a few keV to hundreds of keV. We need a large instantaneous field of view, which with the goal of observing the whole sky simultaneously. We need a long continuous observation uninterrupted in order also to study variation of long-term variation of sources. We need a very good angular resolution of the order of arc minutes to provide coordinates to optics and observatories, and possibly a better subarc mean point source location accuracy. We need a moderate large effective area if we want to observe transient events, which translate in a good sensitivity. Here I'm using the Crab unit, which are common in the X-ray community. Anyway, sensitivity of 10 at -8 erg square centimeter per second. We need photon by photon capability in order to perform in deep timing and spectroscopic analysis of the events, a good energy resolution, and very good time resolution of the order of microseconds, tens of microseconds, and of course also negligible dead time, especially if we want to avoid saturation for really intense and important transient events. Why the moon? Our moon offers, of course, not atmosphere, which allows for X-ray observation from the surface. Depending on the position of an observatory on the moon, it allows for full sky or half sky accessibility on a long time, a very stable environment, which is good for angular resolution and point source location accuracy, and continuous operation. Of course, the moon also offers a large room for resources like volume, power, telemetry, and the possibility to assemble a very large instrument, too large to be put on a free flyer in a modular way, and also to service the instrument during time. Also, with respect to, for example, of high elliptical orbits, which can allow for continuous operation and full sky observation, the moon has a mild radiation environment, meaning that the X-ray detectors can live for a long time with moderate cooling. So the idea is to develop a very large permanent X-ray observatory called LEM-X, based on the collid aperture X-ray imaging, and operating in energy band between 2 and 50 kV. Each camera is equipped with a detector tray made of silicon drift detectors, and is capable of monitoring both from the imaging, timing, and spectroscopic point of views, a very large field of view, more than 2 steradians per camera. The camera is thought to be completely modular. For example, also the backend electronics and power supply unit are integrated in the camera. So that means that the instrument can operate with incremental performance, starting already from the installation of the first 1 or 2 cameras, of course, with a limited field of view and limited sensitivity. The goal is to reach a complete dome, like the one you can see on the left side, composed from number of 30 cameras, in order to have high sensitivity monitoring. And of course, the astronaut is not included in this project at present. This is a representation of the camera, which is the design is we will see is already in advanced state, and as I said, the detector is based on a silicon drift detector, which allows for point source location accuracy of 1 arc minute and angular resolution of 4 or 5 arc minute, depending on the optical design of the camera, and a very good energy resolution, and also very good sensitivity. The resources are quite good. The camera is compact, 35 centimeters, is lightweight, about 15 kilograms, and the power consumption is about 15 watts at present. We are working on this project in the context of the PNRR, which is the Italian Recovery and Resilience Plan, and in the framework of this project, we are now developing the detector tray. Anyway, the whole camera design is based completely on the heritage of the WFM that we developed for the LOFT ESM3 mission for the phase A study, and now also the same design, camera design, will be on board on the XTP Chinese European mission, which shall be launched at the end of the 20s. The project will be completed by mid-25. And these are just a few snapshots of the technology. These are the large area silicon drift detectors developed. This is a very large detector, monolithic, 7 by 7 square centimeter, already developed in a collaboration between INAF, National Institute for Nuclear Physics, and the Fondazione Bruno Kessler in Trento. The readout electronic, both analog and digital, rely on the heritage of the few ASICs, Vega, Lyra, and Orion, that were developed by Polytechnic of Milan and University of Pavia in the framework of the Rexo collaboration. Lyra ASICs will be on board the Hermes constellation to be launched mid next year. It's a CubeSat constellation for high energy astrophysics, while, for example, the Orion ASICs is in the Theseus design. Last point, technological point, which seems simple but is not, is the design of the front end. Being this an imaging instrument, we need a very stable detector plane, so we need to ensure both very low noise in order to reach the required spectral resolution and angular resolution, but also very stable detector plane in terms of thermoelastic deformation, which is very important, of course, on the moon, depending on the site, but the temperature variation could be very large. This is my last slide. These are simulation of a crowded field of the galactic center with several sources that can be observed and imaged in a few kiloseconds. And these are the single camera anticipated performance. Of course, the total performance will depend on the number of cameras and the total design. But as I said, the field of view is very large, very good angular resolution, point source location accuracy. The sensitivity is more than enough to image and perform timing and spectroscopic analysis of transient events like gamma ray burst or X-ray burst or etc. The energy resolution is comparable as an order of magnitude to the best one that you can reach with a CCD, but this is the one important point is that these detectors are single photon detector, so we have this energy position and time information for each single photon, not for the integrated frame. The time resolution also is very good. It's of the order of 7 microseconds, but can be improved to a few microseconds, 1, 2. And also the expected time will be very low for an intense event. So that's all.